Now let's look at some additional applications of segment trees. So here's one problem. It's called subsequences from code forces. So we are given an array of n numbers. So n can be up to 10 to the 5. And each number is between 1 and n. And we are asked to find the number of increasing subsequences that contains k plus 1 element. And k is in the range from 0 to 10. So at most we get k equals 10. So we want to find the number of increasing subsequences with 11 elements. So I think you should be familiar with longest subsequence problem that can be solved using dynamic programming, where the straightforward implementation takes square time, and you can do that in n log n by storing the result a little bit more cleverly, and then use binary search. So, but this problem is if we are willing to do n squared, then it's actually pretty straightforward. So given, suppose we already calculated this for j, so length j, the number of increasing subsequences ending at each element, the number of length j increasing subsequences ending at each element. Suppose we already computed that. Now we want to compute this for j plus 1. So then for each element, we look at all the elements that come before it, and that is less than it. And then we want to sum up all the numbers in them, because if we have a length j increasing subsequence ending at the element before me, and that element is less than me, now that gives me a new length j plus 1 increasing subsequence, and all the length j plus 1 subsequent come from that. So what I need to do is I need to do this sum. So I need to do this sum efficiently, and that's what segment tree enable us to do. So we are trying to sum things, but here again we have this kind of 2D quadrant property, because we want to look at elements that come before me, but they also, those elements has to be less than me, because only then they can help me create increasing subsequences. So and then we want to do the sum. So essentially 2D quadrant sum, if you will, using the terminology that we use in this topic. So that can be done using segment trees. So basically we compute the number of increasing subsequences ending at each position for increasing j value. And while we are going from j to j plus 1, what we can do is we can compute the element in the order of their in their natural order. So basically how big they are. We first compute the smallest one, and then we add that to the array. So yeah, so I guess a fairly straightforward implementation is we have this array, and then we add that result into the segment tree. And then after computed, we can copy it out. I'm sure there are probably ways to make it a little bit more efficient, but this should be sufficient to pass. But yeah, the key is it's essentially a 2D quadrant summing problem while we are computing this. And because the k can be only up to 10, so the complexity is basically n log n times k, which should be enough. So that's this problem. So this is a problem from USICO, the platinum problem called promotion counting. I guess one of the easier platinum problems. So we are given n cows, and n can be up to 10 to the 5, and they are organizing a tree, and the cow one is the root. So then every cow has a distinct proficiency rating, PI, And what we need to compute is for every cow, count the number of descendants, so the number of nodes in the subtree, so that Pj is greater than Pi. So as you can see, there's kind of we are counting things in two dimensions. One dimension is in the tree; it has to be below me, so it has to be in the subtree. The other is the proficiency rating has to be higher. So then the first technique one need to know for coming up with efficient algorithm for this problem. So basically, we need n log n, something like n log n or n log n squared should be fine. But I think this can be solved in n log n. Is to convert a tree into an array. So there are different ways to do it, and this is for this problem we just need the most basic way, which is every node will go to an element in the array. So this is called the tree flattening because so we're flattening the tree into an array. And one way to do it is doing a pre-order traversal. So for each node, we first output that node, and then we traverse its children from left to right. So for example, this array is a pre-order traversal of this tree. And when we do pre-order traversal, it has the property that all the nodes in any subtree are consecutive. So for example, if we look at B, then all the nodes in the subtree of B, it's in this array. Start at B, and anything after B, this rest of the yellow part corresponds with the subtree. So for another example, this blue part corresponds with the subtree here. So because of that, so once we do this tree flattening, we can use an auxiliary array to record the starting and ending position of the subtree rooted in an array. So then for any node, if we want to find information about subtree, we know which segment in the array we are looking for. So once we have that, then this problem becomes something similar. So after tree flattening, we have an array of a proficiency rating. So I use this to try to illustrate this. So the x-axis is supposed to be array, and the y-axis are the proficiency rating. And let's say for this node here, we want to find out in the subtree what rating, how many number of rating are larger than itself. So then the subtree is this range in the array. So I use these two vertical bars to denote. So let's say these are the nodes in the subtree. Then what I'm trying, the question, to answer the question, what we need to do is to count the number of points in this yellow highlighted region. So the y-axis has to be above the current node, and x-axis has to be in between these two boundaries. So this is slightly different from a 2D quadrant problem. It can be viewed as generalization because on one dimension, it's everything above me. But on the other dimension, we have a two boundary. But that's not the problem at all for if we're using segment tree, because segment tree allow us to do this range query. So all this does is this forces us to choose the segment tree must be built on the x-axis. So then we sort based on the y-axis, and then when we add things by the order, when we are query something, we will guarantee that things that are in the array are only things in one side. So I guess for this problem, we'll be adding things based on from high to low. So we will first add this node, then this node, then this node, and then when we are processing this node, when we are querying the array, how many things are in this part, we'll be only picking up these two nodes in the yellow part because these nodes have not been added yet. So so that's why we can use segment tree to solve this problem. So one thing I didn't mention is there's a slightly simpler data structure known as the Fenwick tree or binary index tree. So what it does is allow prefix queries. So most of the problem we have encountered so far can also be solved using prefix Fenwick trees, because it's a 2D quadrant problem can be solved using Fenwick trees. But this problem cannot, because this we really need to query a range. So the segment tree is more powerful than Fenwick tree, and so in some sense, it suffices to learn segment tree, and you don't need to yeah you don't need to have to remember how to do family tree or binary index tree. So that's for this problem. So this is like this is like a 2D band problem, but it's important that we have this. So one dimension we have this half plane, if you will, and the other dimension we have a band, we have a rand. Okay, so I think this is the last example problem I want to talk about for segment trees. This is a problem from Codeforces called the ball, and it's equivalent to this other problem. So it is a fairly classic problem, because as you can see, as you're going to see, it's fairly standard. So it's important to understand how this problem can be solved. So we have n ladies, and each lady has 3 properties: beauty, intellect, and richness. And for each lady, so we want to find out the number of ladies, so that there exists at least one lady who is more beautiful, smarter, and richer. So all 3 is better. So basically, we want to find out for every lady, does it exist someone else who is all better? So in all 3 properties, they are higher value. So so the question is hard or different from the previous example problem, in that now we have 3 properties. So we talk about 2D quadrant. So basically every point has 2 values, and then we know how to deal with that, because we turn one dimension into the indices into the segment tree, and the other we sort. Now we have 3. So how do we do that? So this is like almost like a 3D. I don't know whether it should be called quadrant, but essentially we are querying information about this 3D kind of corner, if you will. So how do we deal with that? And in particular, where does the information in the 3rd dimension go if we are to solve it using segment tree? So because the indices is one dimension, sorting is another dimension, dynamic update, the order of adding things is another, where does the 3rd dimension go? Now, we can solve arbitrary 3D quadrant problem, in fact. So this problem is solvable in part because for each lady, we only need to know whether there exists another point that's in that quadrant. So we don't need to count how many are there. We don't need to sum things are in there. All we want to know is whether there exists a point in there. So this makes the problem solvable. And encourage you to pause and really think about it. But it is pretty hard if you have not, if you don't have extensive experience with the segment tree already. So there's only one logical place for the 3rd dimension to go. That is the value I store in the segment tree. So I can, instead of just counting things, just using 1, 0, now I can put in value in there, and this will keep more information. So here is how this will work. So we sort the ladies based on 1 dimension. So let's say based on beauty, it's from high to low. And then we will process them one by one. And then we map a 2nd dimension into indices, into an array. This will be the base array for the segment tree. So we can do that by putting all the intellect values in the data in an array. We sort them, and then given any value, we can use binary search to find the index. So we can convert each value into an index into the array. Now, what we are going to do after querying is we are going to put the 3rd dimension into the segment tree. Now, now suppose we have that, what do we need to query? So when we are querying, we are trying to find out whether there's someone who is a higher value in all three dimensions. So we know that any point we will process so far have higher value in one dimension. And then we can choose half in the segment tree, and those will have higher value in a second dimension. So we look at those points. Now all we need is just the max. So if the max value there is higher than me, then I know there's someone there that's higher in all three dimensions. If the maximum of the value is less or equal than, then it doesn't exist. So therefore, the query we need to answer is a range max, so which segment tree can support. So that's how this problem can be one way to solve this problem. I think this idea of putting this information into the value in the array, that's important information. So I remember seeing something similar for dynamic programming, where the state, if all you need is binary information, true, false, sometimes you can put the information into the state. So then this will reduce the state space. So this is have a little bit similar flavor to that. So to recap, we've seen these applications of segment trees. We support efficient range queries of associated functions while allowing point update. So this is what is basically designed to do. If you have dynamic updates and then you want range queries, you use segment tree. But then these data structures enable us to solve a bunch of other problems. So this is a 2D quadrant problem. So given point with two property, we want to query information about one of four quadrant. And then we've seen that we can actually also, doesn't have to be exactly quadrant, we can actually support a band. So we have, on some dimension, we can have both a left and right band. And we've also seen this 3D quadrant problem, but here the query we can support is only whether it's empty or not. So this is the ball problem. And we've seen sometimes we use segment tree to speed up computation in dynamic programming, because when you are computing things, you may realize, oh, I want to count this, or I want the max or mean. So then in some range, so then segment tree can help that. And we can apply segment tree to arrays generated by tree traversal. And in fact, so I didn't talk about that, but there one way to solve this efficiently compute LCA, so least common ancestor, is to use a segment tree and tree traversal. So that may be covered in a later topic. So that's it.